Hi, my name is Cody Ray. Together, Kyler Lee and I performed our heat transfer project on some thermoses. So our project was to determine the effectiveness of a more expensive thermos versus the typical styrofoam and plastic cups you can get at a convenience store and gas station, and ultimately to determine if it was cost effective to buy the more expensive brand. Here are some pictures of the mugs that we used for our experiment. On the far left is a mossy oak camping mug made out of stainless steel, and the two on the right side are cups that you can pick up at Great Scott's, which is a convenience store here in Rexburg. Obviously, more cost effective in the short term would be the cheaper mugs from the convenience store. You can buy about 55 of those cups for the price of the metal mug that you see on the left. To eliminate inconsistencies in data, these tests were carried out in the same location on the same day. The experimental procedures go as follows. 1.5 cups of water was heated to 65 degrees Celsius in each of the respective cups. After placing the lids on the cups, we used thermocoupled and infrared heat guns to measure the surface temperature and water temperature at the beginning and end of the 30-minute or 1800-second increments. Firstly, the stainless steel mossy oak thermos was tested. Thermoses are vacuum sealed in order to reduce convection through the walls of the thermos, resulting only in radiation through the walls. Since we were unable to get the temperatures inside of the vacuum seal, we made assumptions that T1 equals the temperature of the liquid and T2 equals the temperature of the outer surface of the thermos. The overall heat transfer was calculated by using the equation Q equals mass times specific heat times the change in temperature over the change in time. The heat transfer through the vacuum seal was calculated using the gray body radiation heat transfer equation as shown on the left side of the slide. The heat transfer through the lid on top of the thermos was calculated by obtaining a Nusselt correlation with the Grashof and Rayleigh's number, and then applying the heat transfer coefficient into the equation Q equals HA delta T. The values of these equations are shown on the table in the middle, showing that there is a heat loss of 2.43 watts through the wall, 2.18 through the lid, and a total of 2.47. Our numbers don't quite add up, but here in the coming slides we'll talk about some discrepancies as to why we feel that happened. Following the thermos, similar calculations were performed on the paper and styrofoam cups obtained from a convenience store. Other than the material, the primary difference between these cups is the type of heat loss through the walls. In the thermos, there was a vacuum, which means only radiation would be the heat loss, and in these cups, there would be transient conduction. The overall heat transfer and the convection through the lid were calculated in the same way for all three cups. But for the paper and styrofoam, after several hours of research, we were unable to find a standalone equation to calculate the transient conduction through these walls. So to obtain these values, we used the overall heat transfer coefficient and found the difference between that and the lid to obtain the overall wattage loss through the walls. As you can see on the charts on the bottom, the styrofoam had a total heat loss of 7.57 watts, and the paper had a heat loss of 12.35 watts. Here are the tables of data from our Excel spreadsheet, which we used to run our calculations for each of our cups. In the top left table, you'll notice that we have highlighted the total Q values and also the change in water temperature over the 30-minute period. We highlighted these just to show a representation, just so you can see in context of the effectiveness of each of the cups. And clearly it shows that the mossy oak thermos has, not only does it have the fewest degrees change in temperature, but it also has a very low heat transfer loss through this time period as well. Reflecting on the experimentation with the mossy oak thermos, there was a large error in the heat loss due to radiation through the walls. This error comes from the neglection of conduction and convection which occurs in the heat loss. The conduction comes from the supports that keep the inner surface fixed into place as to avoid breaking and wobbling while being used. The convection comes because it was determined that this is not a perfect vacuum in the thin layer between the two surfaces inside of a thermos. And because of that, the convection offsets the calculations. Due to this convection, our assumption that T1 equals the temperature of the liquid, and T2 equals the outer surface temperature are incorrect. A large issue that we faced during this project is the lack of Nusselt correlations for convection of a vertical cylinder. We spent several hours researching on the internet and in textbooks, as well as consulting Brother Danes to find the best solution of how to handle this. And ultimately we found that really all the Nusselt correlations are for horizontal cylinders, and there has not been much work, surprisingly, done with vertical cylinders. After making this determination, we had to assume that our calculations were incorrect, as we only assumed there to be radiation for the heat transfer. Though most of our equations provided wrong answers, they do serve the purpose of showing the advantage of purchasing a more expensive thermos over buying a styrofoam or paper cup for your hot cocoa. Pursuing the issue another step, if you're faced with the choice of styrofoam or a paper cup, styrofoam is a clear winner due to its far substantial heat loss